Infinity. What is it exactly? Not quite a number, yet more than a concept. The idea of infinity has perplexed and excited philosophers and mathematicians since the ancient days. But do we actually understand it? Before we dive into the infinite, let's first get acquainted with some of its quirks. Let's start with a thought experiment set forth by David Hilbert in 1925. Imagine a grand hotel, so large that it contains an infinite number of rooms. Specifically, every room is numbered, starting from 1, 2, 3, and so on. And in this hotel, there is no upper limit to the number of rooms. Now, imagine that this grand hotel is completely full. That is, every room has a guest in it. An infinite number of rooms accommodating an infinite number of guests. Now, a man walks into the hotel, up to the receptionist at the front desk, and requests a room. The receptionist kindly tells the man that the hotel is completely full. Just then, however, the manager walks by, telling the man that they can definitely find him a room. The confused receptionist asks how that could be done. And in response, the manager knocks on the first room of the hotel and asks the guest to move to the second room. The guest in the second room would then move to the third room, and so forth. As the guests are switching to the next room, the man enters the now vacant first room. The hotel is completely full, again. What is strange about this is that the addition of the new guest did not change the total number of guests. What started as an infinite number of guests ended as an infinite number of guests, despite adding one. But the story is not over. The receptionist, glad to see things settling down, looks up to see a crowd of people entering the hotel lobby. One person approaches the front desk and declares that there are an infinite number of people lining up outside that all need a place to stay. The receptionist prepares to dissuade them. However, once again, the manager interrupts to say that of course they can make space for them. He proceeds to then knock on the first, second, and third doors, telling the guests that they will all be moving to the next even-numbered room from their own. This message is passed along to all of the guests as they all begin to shift over to even-numbered rooms. This leaves every odd-numbered room open, which then begin to fill with the infinite crowd flowing into the hotel. So, how many individuals are in the hotel now? 2 times infinity? A bigger type of infinity? The counterintuitive answer is that the Grand Hotel is still just as filled as it was before. Every room had exactly one guest before, and every room will have exactly one guest after. So what's going on? It's useful to consider 2 different types of numbers: ordinal numbers and cardinal numbers. Ordinal numbers describe the order something is in, and are analogous to terms like first, second, third, and so on. Cardinal numbers, on the other hand, describe how many of something there are, like 1 apple, 2 oranges, 3 pears, etc. We can then start to think about things in terms of groups, where the number of items in a group is called its cardinality. This group also has a special term in mathematics. It's called a set. This first set has 7 numbers, and so has a cardinality of 7, while this second set has 3 numbers, or a cardinality of 3. You'll notice that set A actually includes the numbers that are in set B. So we can say that B is actually a subset of A. Let's add another set, C, which also has 7 numbers. Now these numbers are different from set A or B, so there are no subsets of C here. However, both A and C have the same cardinality. They each have 7 numbers. So far, this is all pretty straightforward when we have small sets. But this video is about infinity. So let's adjust our sets. Let A be the set of all natural numbers. That is, every number starting from 1, 2, 3 onward, without any upper limit. What is the cardinality of the set? To be more precise than just repeating the word infinity over and over, we can use a special symbol reserved for the cardinality of infinite sets. Aleph. Aleph, which is the first letter of the Hebrew alphabet, can be given subscripts to describe the cardinality of different types of infinity. More on that in a moment. The natural numbers are called countable numbers. That is, if time had no end and we were immortal and very bored, we could, in theory, count through all these numbers. The cardinality of the natural numbers is called Aleph null. So what happens if we take a subset of the natural numbers, perhaps by retaining only the even numbers? This is clearly removing half of all the numbers we started with. So what is the cardinality of this new set? Its cardinality is still Aleph null. The reason why has to do with something called one-to-one correspondence. It works like this. Place these two sets side by side, the natural numbers and the even natural numbers. For each natural number, you compare it to an even natural number. This pairing, called a bijection, shows that there is actually the same cardinality between these two sets. We can go the other way too. Right now we are looking at the natural numbers, but we can also consider all integers. At first, you may think that these sets won't pair together, since the set of natural numbers is a subset of the integers. However, with a little rearranging, you can see that every natural number will pair nicely with every integer, making the cardinality of the set of integers Aleph null. What about rational numbers? These are numbers in between integers. They are fractions. What is the cardinality of that set? It's a little more rigorous, but you can show a one-to-one correspondence with integers, meaning that this set has a cardinality of Aleph null. So can we ever get past Aleph null? To answer that question, we need a little more context and another video. So stay tuned as we continue our conversation in part 2.